So, yes?
So work in is work done on the system, and work out is work done by the system?
Yes. System and its properties. So we ended last lecture here. So a boundary can move or change. So I want to underline that. And a system and its properties, and we have to have, the system has to have a quantity of mass or matter associated with it. I can't, you know, in principle, maybe you can define a system as a vacuum, but it's really hard. But let's not say that that's a system. Really, we need mass in it. So a pure vacuum doesn't really work because it's nothingness. So you can't. But let's not get into that. But let's just that philosophical argument. Let's just, you know, let's go with the standard approach where we're not making arguments. A system has to have a quantity of matter associated with it. In order to define a system, I need to be able to separate the system from anything else, i.e. the surroundings, so I need to have a boundary. And this boundary can move or change. So if I blow up a balloon, if I consider the polymer part of the balloon as the boundary that separates the air inside the balloon from the air outside of the balloon, as I blow up the balloon, what happens to the boundary? It gets bigger, 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 right? I deflate it, I pop it. If I pop it, what happens? I have a new exit port for air. In fact, the whole boundary can shred and I no longer have a system. I destroyed the boundary. So, if you're working on jet aircraft, you can change boundary conditions to destroy the aircraft. Right? Change the boundary conditions of fuel going into the engines and you'll crash. Whatever. There's a lot of ways. You change boundary conditions, you change the mathematics, you change the properties, you change the thermodynamics. So the boundary, the coupling or the marriage, or the trilogy of the boundary, system, and surroundings is very important. So properties of the system. So I've already wrote down some of them. So temperature, pressure, volume, mass, N is the number of particles. So instead of mass, so this is a quantity of matter. So if I say that there's a mass per particle or something like that, right? So, and then there's some extra properties, density, thermal conductivity. So thermal conductivity is K in book. So we use K a lot in mechanical engineering. Physics uses this capital omega, lambda. Viscosity, etc. So I can do a lot of other properties. Has to be a volumetric property. So surface tension doesn't apply to a property of the system. It's the property of an interface. But viscosity, right? Thermal conductivity. So what's another interface? So it needs to have, you know, so you need to have a volumetric based property. Heat capacity. It can't be a surface tension. That's a property of the interface. It's not a property. A lot of times you say it's the property of a fluid, but really it's property of the interface. So related to properties, let's just draw another system related to, let's do another thing more realistic. So let's consider that I have a piston. Okay? So I have a piston. Now I'm just drawing a, so this was a blob, just very general, so let's do something a little more specific. So a piston. So I have a piston system, and I'm just drawing a schematic before I write out full energy balance. And now I have to define a boundary. So I can define a boundary just on the gas, and so my system is just the gas inside my piston. Or I could draw my boundary as the entire engine with the gas inside. I can draw my boundary different ways. So if I do it boundary method 1, then my surroundings are the cylinder outside, all the stainless steel, and all the air outside of that. My surroundings consist of everything outside the boundary. My system is only the gas inside. If I do this case, then the stainless steel walls of my piston and the gas inside are my system. And then everything outside is my surroundings. So right here I have it like such. Now what happens to a piston? Right? So sometime later, I can have my it moves up. What happens to the boundary? So we'll just do it for one. My boundary expanded. My system changed boundary. When the piston goes up, is that work out or work in? Piston went from here to there. It's work out. When I compress the gas, I'm doing work. When I have the explosion reaction, it does work out. So you can see that my increase, I had an increase in volume. So anyway, so there's this change in volume, and then I can look at this stuff and we can go over whether it's work in and work out, and then I can kind of go over what your question about sign conventions and boundary work. So when I drew it like such, I'm going to have boundary work. I have a change in boundary, and so if I blow up a balloon, I do work on the balloon, and then the balloon does work on the surroundings. I had to displace all that air. I had to do work to blow up the balloon, and the work then did work on the surroundings. Now, say I suddenly am weak and I can't keep all that high pressure air in the balloon. The surroundings does work on the balloon, and the balloon does work on me. It puts air back in my lungs when it went the other way. You can see how there's this coupling between, and I'm just using boundary work as an example. So, yes?
So for boundary 2, I understand for boundary 1, the work being done by the system is on the piston going up. But for boundary 2, what is the work being done by the system?
Well, it's the same.
So it's still on the piston itself?
Yeah, well, all I did is displace the stainless steel. But if I don't have thermal expansion of the stainless steel during a power stroke, then the stainless steel part of the system didn't do work on the surroundings. So typically you have an engine, it operates, it heats up, there's expansion of your engine. So really that small amount of expansion of your engine during heating up is doing work on the surroundings. But in this case, I can draw the boundary like that, but it really didn't change. I could break the area, the volume within that boundary into two parts, one of the cylinder and one of the gas. And then you would see after inspection by breaking it into two parts that the volume of the chamber cylinder part didn't do anything. So it really was just boundary work associated with the gas, while the piston did move. Now if I have thermal expansion that comes into play, that's a whole nother issue. So there's a lot of systems where you can have changing boundary conditions not associated with what we really want, but some component of it. And then you need to take that into consideration when you look at efficiencies. Yes?
So it really, the negative or the positive part of the equation really comes from where exactly you were looking, the perspective of the system. So
from the perspective of the system, yes.
So we will always be given a very specific, which system are we analyzing?
Not always. Sometimes you need to, not very specific, sometimes you need to define that yourself. That's why I said the step 1 is always to draw a schematic. Because if you can't draw a schematic, then how are you going to know whether heat in or heat out or there's work in or work out? You have to be able to draw a schematic. And so that takes time and practice. So my recommendation is just pick random things and draw a schematic of it, and then write out full energy balance and simplify it for that. That's the best way to learn it. Just pick something random. And if you don't want to do random, you just do problems in the back of the book, and you follow my approach of drawing a schematic and writing out full energy balance and simplifying it. Okay, so here are my system and properties. And so there's you can break down properties into two subsets, intensive properties and extensive properties. So intensive properties are independent of mass, and extensive properties are dependent on volume. So another way to look at it is extensive properties are additive, and intensive properties are non-additive. I used to always get these mixed up on what was what. I knew one was additive, one was but I could never, I used to always get them mixed up. In a couple slides, I'm going to talk about the state postulate. Now I never forget it because I know the state postulate because it's foundational to thermodynamics. And I remember that the state postulate has to do with intensive properties. And I knew two intensive properties that always work for the state postulate, and I know that they were non-additive. But anyways, we'll get to this. So these are in and a pass or non-additive. So let's look at a system here, and let's just write temperature, pressure, mass, number of particles. Thank you. Temperature, pressure, mass, number of particles. I could also put viscosity, thermal conductivity, density, whatnot. Let's put volume here. So I have my system, and it has all these properties. And let's say this is my system at T0 equals 0 seconds. And so I can draw an arbitrary boundary or segment line that separates my system into two subsystems. Not changing the properties, but I just put something in. And let's say I do it in the middle, so this volume is the same as that volume. So then I can break this off as TA, PA, TB, PB, mass A, volume A, mass B, volume B. I could do more. So when I put this boundary here, so I have mass initial, extensive properties, dependent on volume, and are additive. So mass equals mass A plus mass B. That works, right? As soon as I put it here, I can distribute on the amount of mass on each side. Right? I have a total mass here. I can put this here. And the total mass here has to equal mass A plus mass B. Dependent on volume, additive. So I could do the same thing. Volume equals volume A plus volume B. So let's put temperature equals temperature A plus temperature B. Pressure equals pressure A plus pressure B. If I take this room and I put a divider between it, and over here I give a temperature, and over here to get a temperature, then I immediately remove this temp. Can I add both these temperatures to get the temperature of the room?
No.
Yeah, so this, you can't do that with pressure. Some things are not additive. So temperature and pressure are not additive. Can I do it with the number of particles? Yes. Can I do it with density?
No.
Can't do it with density. Can I do it with thermal conductivity? No. Can I do it with viscosity? Yeah. When we want to deal with these temperature, pressure things, we have to do volume weighted averages or mass average properties. So there are ways to add TA and TB and PA and PB, but we can't use big P. We have to use some other coupled variable. So I had my state of the system here, and then I broke it. I put this divider in, and then so I can define the state of the system at T equals T0 at 0 seconds. And so I have my pressure at some initial point in time. So this is just some snapshot in time. I take a snapshot in time and I say, this is the average, system average temperature, pressure, mass. So I don't have to say average mass, but I could just say, this is the mass of my system at T equals 0. This is the group pressure and temperature. Right? This is the volume of my system at T equals 0. So you can immediately see that in order for me to do this, I didn't have to say group volume. at T. I could give a specific volume. I didn't have to say like an average thermodynamic macroscopic mass. No, I could say the mass of the system. But in here I had to use words like this is the average system behavior pressure. I might have a small fluctuation in pressure over here versus over there, but if I average over, integrate it over, I get an overall pressure of the room. With mass, I'm not going to have a fluctuation in mass. I guess if I define a small control volume over here, I might have a small fluctuation in mass. But in general, I would just say this is the mass over here and this is the mass over there. This is the volume right here. This is the volume over there. I'm not getting fluctuations in those. So, equilibrium of the system. So if I look at two snapshots in time, T1 and T2, and T2 equals T1 plus some delta T, okay, and let's just say delta T is on the order of 1 nanosecond. So I can look at my system at T1 and it has a pressure, a volume, temperature, and mass. Now if my system's at equilibrium over a I put nanometer, it should be nanosecond. Over 1 nanosecond, I say over a nanosecond snapshot in time, or time interval, my system is at equilibrium. So then at T2, I have so over short time intervals, it looks like my system's at equilibrium. But if I were to find that this nanosecond is away, so if my temperature is changing over a nanosecond, then I could say that the system's not at equilibrium, at least thermal equilibrium. So I have equilibrium system, and what I really want to do is I want to say that the properties are not changing in time. Now, if I want to say it's at equilibrium, I don't have to use a nanosecond. I could use 1 hour. So probably in the middle of the night, at midnight, in this room, I could look at the temperature and pressure in this room, and it wouldn't be changing in time, right? So I could probably do several hours, and the temperature and pressure, volume of the room, mass of molecule, wouldn't be changing, if any, very, very little. However, we look at the temperature and pressure in this room as a function of class time. We're going to see that it's going to heat up and cool down. So over a course of 2 hours, I could say that the temperature and pressure in the room is changing. But if I look at every nanosecond, I don't see any changes in temperature and pressure. So on a very short time scale, it looks equilibrium. So equilibrium is coupled to the time period of interest. Not changing over small changes in time. Yes?
So in a case like that, you would just cancel out the delta T because it's negative.
Yeah, well, we just say that it doesn't matter. So, yeah.
There's no change.
Yeah, I'm just illustrating that if I want to dictate these things, I need some time reference.
Got it.
Yeah. I could cancel out, yes. So, types of equilibrium. There's many types of equilibrium. For thermal equilibrium, it's constant temperature. For mechanical equilibrium, it's constant pressure. For chemical equilibrium, it's constant AB, AB. And why do I say that? So it's distribution of particles. If I can have reactions, so if I just do this, A, B, A plus B. So if there's chemical equilibrium, I no longer have reactions taking place, so the total amount of species A is constant in time. The total amount of species B is constant in time. The total amount of product species AB is not changing in time. Phase equilibrium, I have constant. So if I take something at the triple point where I can have, or not at the triple point where I can have mass, water, and vapor all exist at the same time. If I'm at phase equilibrium, I'm going to have a constant mass of ice, constant mass of water, constant mass of vapor. Okay, so if I take a glass of water and put it on the table, it's not going through any phase transformations at room temperature. So I'd say the constant mass, and I draw a boundary around my water, I'm going to say that it's all water and it's staying all water. It's at phase equilibrium. So constant phase. So I take water, it can be in 3 different phases: liquid, vapor, and solid. From at phase equilibrium, those relative distributions of those phases don't change in time. So this is why I wanted to get to the state postulate. So the state postulate is very important. The state of a compressible system is specified by 2 independent intensive properties. Two independent intensive properties. Intensive. We already discussed that temperature and pressure are intensive. We can't add them. They're not additive. If I take, this is 40 sheets, this is 3 sheets. If I tell you the temperature of this paper, and then I heat this one up, and then I combine them, I can't say 40 sheet versus 10 sheet added together gives me TA plus TB. It doesn't work that way. I need to use heat transfer to dictate how these temperatures change. And that's dictated by the amount of mass of each of them. I can't just add them. Same with pressure. Let's use a gas. I have a volume of gas in this jar. I have a volume of gas in another jar. I mix the jars. This one has a certain pressure. This has another pressure. As soon as I mix them, I can't do A plus B equals the final pressure. So state postulate. So if you recall in the wording on the first law of thermodynamics, it started out, there is an equation of state of the system called the internal energy. If you recall for the second law of thermodynamics, how it was worded, the first sentence is, there is an equation of state of the system. State postulate. You know what an equation is. F equals ma is an equation. Right? The first law of thermodynamics written out as an equation. State of the system, now we're talking about states. So there is a way, there's an equation that we can define to define the state of a system. We're saying that the internal energy is an equation of state. In order for me to say that it's an equation of state, I need to apply the state postulate. So that means in order for me, any equation I derive to describe the internal energy, which is, because it's a state function, I need 2 independent intensive properties. I can have more, but the requirement is if I draw U is equal to something, and I put it in equation form, so let's just do that. U is equal to a function of 2 properties. I know I need 2 independent intensive. So I can put temperature and pressure. I can grab another independent intensive property, but I need 2. So U is an equation. There is an equation to say the system called the internal energy. So state postulate, I need 2 independent intensive properties. We're always be using temperature and pressure in thermodynamics because they satisfy the state postulate, and if you remember what I just said several times, the first 2 laws of thermodynamics, they start out by saying we can define an equation of state of the system. So everything else is based on the fact that you can define the state of the system at some snapshot in time, and then what you do is you look at the state of the system at some later time, and you analyze whether you need to do work to change it, or it did work on you, or whatever the efficiency might be. My aircraft is sitting on the runway, or it's sitting before people get loaded in. There's a state to the aircraft, right? People get in the airplane, there's a new state to the aircraft. It's idling, aircraft's idling on the tarmac before takeoff, it's at a different state. Aircraft is on takeoff, it's at a different state. Aircraft is moving at constant velocity at 10,000 feet, it's at a given state. We'd have to break down all the pieces of the aircraft into individual components and define the temperature and pressure, and then we could get the total internal energy and entropy of it. But if we knew what all the components of the aircraft are, from the rubber to the people to everything, and we knew the temperature and pressure, we could define the internal energy of everything within. Because everything has an internal energy that has matter associated with it. So temperature, pressure works. I could use temperature and density. We already talked about density, wasn't additive. We could use thermal conductivity, temperature and thermal conductivity too. But, you know, what do we use? This one. Yes?
For the third equation that you have in the state postulate, is that pressure or density?
Density. This one's pressure. The last one's pressure. This one's density. Okay, so now I have this. I define the state postulate. Very, very important. In order to define the state of a system, you need to know two independent, right, intensive properties. So property A, we'll say, is pressure. And this, we're going to say this is temperature 1. Thank you, sir. Okay. So we'll say property A, state 1. And we're going to bring our system from state 1 to state 2. And there's going to be a path associated with going from state 1 to state 2. And I've said that I'm going to do a diagram like this. Property A, pressure of the system. Property B, temperature of the system. So right here I know T1, P1. Right here I know T2, P2. I did this like such because then I can easily justify that I know the state of the system here. State 2, state 1. And so state 1 I can say is at t equals 0, and state 2 is at t greater than 0. So I take a snapshot, beginning of my process, I have a given temperature and pressure. I might do work, the system might do work on me. I might add mass, the system might lose mass, whatever it might be. Sometime later, it follows some path. That path is dictated by the mass and heat and work added or removed from the system. I get to a new state. No, I can take another path. State 3. So now if I look at this path, this was a constant temperature path. So these paths can change. So the path process, so I can have an isothermal process, constant temperature. I'll just say path 2 and path 1. Isobaric, constant pressure. Isochloric, constant density. So let's just draw one that's isobaric. State 4, path 3. Okay. Get the general idea. So we're just drawing. I'm indicating that I can have a state to the system. I can represent that state of the system as a point on a graph. There's a path that I have to take to go to here. And so this represents the change in temperature and pressure of my system as it goes from state 1 to state 2. This is, when I draw it like this, that change in temperature and pressure is represented by a path taken. If you notice, I can't just go immediately from state 1 to state 2. It has to be continuous. I can't just increase the temperature and pressure instantaneously. I have to have some continuous variation. So that quantum mechanically, we could go from state 1 to state 2 without a path, binary flipping a coin. In thermodynamics, we can't exactly do that. Yes?
Is isochloric the same as constant volume?
No. Constant density.
Is there something for constant volume?
Constant volume process. What was it? ISO, I don't know if maybe it's isovolumetric. Doesn't sound right, but maybe. There's probably a name for it. I just don't remember it. So
Volume isn't an intensive property.
what's that?
Volume isn't an intensive property, no.
So you can still have a process that you can still have a process.
Yeah, you can still have a constant volume, but it wouldn't be part of your state postulate for the.
Well, this right here doesn't. What I'm drawing here, I'm not trying to say anything about the state postulate other than the fact that I need to know two intensive properties here and here. And if I decide that I want to know some property there, I also need to know the temperature and pressure or two independent intensive properties. But I can have a path that's constant volume. This path here, I could say that it was constant volume and constant pressure. I could draw another path and just say that it was a constant volume process. And then for a constant volume process, given that what the system was, if it's an ideal gas, I can draw that temperature and pressure relationship. Right? So if it was a constant volume process, since you asked, and it's an ideal gas system, I have PV equals M R gas T. So we say it's a constant volume process, there's no mass added. So we're not going to talk about mass transfer. So it's constant volume, constant mass. Oh, then it is constant density. Yeah, I guess you're right. But yeah. So if this one would be constant volume with no mass flow. Isochloric. Yeah. Okay. Given the mass didn't change. But I can have an isothermal process with mass added and removed. I can have an isobaric process with mass added. And I can have an isochloric process with mass added and mass removed. Turns out if I don't have constant volume process, isochloric. Okay, good question. Process. Any change to the system goes from one equilibrium state to another equilibrium state. That's a process. Isochloric, I go from one equilibrium state to another equilibrium state. That just meant that I go from these different states, what we just talked about. If it's a constant mass process, then if there's a process and there's no mass, being exchanged, and it's constant volume process, then it's an isochloric process. If it's just if the sole thing is a change in temperature or no change in temperature, right, constant temperature, it's an isothermal process. The path, how the process takes the system from one equilibrium state to the next equilibrium state. So these two are coupled to each other. If I change the process, I change the path, or vice versa. If I change the path, I change the process. It's not really a chicken and egg. It's really change the process. Result is a different path from one equilibrium state to the next. Yes?
So to apply this, we would take like using the example of a piston engine, you would have the state at ignition followed by the state when the piston reaches bottom dead center.
Sure. Yes.
And combustion is complete, and then you would have, so that would be your first equilibrium and second equilibrium, and then we would have another process for the exhaust stroke when the piston.
Yeah, you'd break it all down. You'd break it all down into, and so if you have a 4-stroke engine, you have 4 processes.
Yeah, a 2-stroke engine, you would have 2 processes.
A process where the properties, so quasi-equilibrium or quasi-static process. This is a process where the property systems change at a very slow rate or very small increments. Thank you. So quasi-equilibrium. So if I look at, I talked about this room, and I looked at before everybody was in the class till after, if I look at really small snapshots of time, right, every minute, in that case, I could probably say, well, let's not do a minute. Let's do every, millisecond. I look at the temperature and pressure in the room, we would see that every millisecond, the temperature and pressure in the room are not really fluctuating. They're pretty much constant. But if I look over the course of the whole room, would see that the room temperature increased, right? So given that I can say that it goes from one equilibrium state to another equilibrium state to another equilibrium state to another equilibrium state, I can say that it's a quasi-equilibrium or quasi-static process. Now, if I put, I don't know, I don't want to say anything dangerous, but, you know, if I put a, you know, I'll just say it. So if I put, I don't want to, if I put a bomb in here, I don't know, I don't like saying this for some reason, but if I put a bomb in the room and it goes off, we could see that that explosion is not a quasi-static, quasi-equilibrium, right? There's going to be sudden changes. Yeah, put fireworks, yeah, thank you. So when we drew these paths, the temperature and pressure were changing. When I go back, oh, well, I can get to that in a second. If I go back to this graph, I drew these different paths. When it's quasi-static, so temperature and pressure are changing in time, because I'm going from one equilibrium state to the next equilibrium state. If I break each one of these down into substates, I would say that it was equilibrium at each substate. There's no large fluctuations in temperature and pressure there and there, but it follows a path to change those. So what we assume in thermodynamics is that there's always quasi-equilibrium. You have to do non-equilibrium thermodynamics. So we assume that things happen through a quasi-static process, where there's quasi-equilibrium. Even though we are increasing the temperature of the system, it's happening really slowly, so we can just look at the two initial and final states and we don't need to take into account those changes. We can follow a smooth path. So one going from one equilibrium state to another, so I can say at some time P equals T1, I have the same pressure and temperature at some, and let's just say delta T is equal to 1 picosecond. And so related to this, I can say P at T2 is equal to P at T2 plus delta T dot 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 P at Tn is equal to P at Tn minus 1 plus delta T. And likewise, I can do the same here. And then when I get all around, this gets all said and done, I get the pressure at T1 does not equal the pressure at Tn. So Tn would be my final state, T1 would represent my initial state. But if I look at each individual process, I could say that over a small snapshot in time, 1 picosecond, it looked like it was at equilibrium. So the magnitude of this delta T is relative to the requirement that this is valid. So it's size and system and everything dependent. So some systems, 1 femtosecond isn't enough. For some systems, say the universe, right? If I look at the sun, equilibrium state of the sun, I could probably say that 10 years, I could use 10 years as a delta T. Yes?
As far as your definition goes, you said P of Tn is equal to P of Tn minus 1 plus delta T.
Oh, it should be plus.
P of T2.
Yeah, it should be plus.
Oh, okay.
No, it should be minus. I was right, yeah.
But then you have P of T2 is equal to P of T2 plus delta T. Shouldn't it be P of T1 plus
Yeah.
delta T?
Yeah. It should have been minus there. Thank you. Okay, so now we're talking about processes in paths. So someone just asked a question about an engine and the different parts of it. So most of our systems that we use in everyday life are processes that go through cycles. So in words, a cycle is a process that takes the system away and then back to its initial state. Initial state initial equilibrium state. Okay, so we can talk about non-equilibrium cycles. That's really complicated stuff. Let's just stay in the equilibrium realm of thermodynamics. So we have all states are, we can define a state as something non-equilibrium, that's a whole other area. But let's just say we take a process and we go from initial equilibrium state, we take it away from that initial equilibrium state, and then we bring it back to initial equilibrium state. So let's draw. So now I'm going to do pressure and volume. And so I'm going to say P1, and I'm going to have some volume 1. And right here I'm going to say it's at state 1. And I can say it's at state 1 at t equals 0. And then I follow some path. And I'll call this path 1 to 2. And then I end up at some state 2. So I got a volume 2 and a pressure 2. And so this is at some T2 greater than 0. So I brought it from one equilibrium state, and I brought it away, and then I bring it back. And call this path 2 to 1. And then I'm back here at some later time, T3 greater than T2. So I went through a cycle. I'm right back to my initial state. So I always ask this question, what for a cycle can the internal energy change? What is delta U of a cycle? 0. Now I asked that question on finals, and I don't know how many times people answer it wrong. So I'm trying to do a better job at focusing on this early on. But so I have a path, I come back, and then I have some area inside this curve. So if I go from state 1 to state 2, I could get another area underneath. And then if I go from path 2 back to 1, I have an area under this red curve. And if I subtract this area, path 1, the area under the curve under path 1, 2, from that area, I get the area within my cycle. Okay?
What is the area within the cycle represent?
Yeah, so that's the important thing. So you guys took calculus for a reason. It's because volumes, areas, lengths of lines, rates of curvature, all these things that you use with calculus to calculate have, in a certain context, have meaning. And so in this case, in a PV diagram, this area is important. And you can see these are really goofy curves. So you'd need to use calculus to calculate that area. You could approximate it with a bunch of straight lines, but you need to know areas. And so when I have a PV diagram, this area represents work. Boundary work. Remember I talk about blowing up a balloon? So I increase the pressure and volume, I decrease the pressure and volume. Now there's a nice sign convention that I like to use, and if you look here, this is, I'll do it here, counterclockwise. Now I use the clock analogy. So if I have my clock on the wall and I put my finger in front of the seconds hand moves my finger. Which way?
Clockwise.
Is the clock doing work on me or am I doing work on the clock? So clockwise represents work by the system. Now if I want to make that clock go in reverse, I have to do work on that seconds hand to make it go backwards. So I do work on the clock. So counterclockwise in a PV diagram represents, no, it's not work out, it's work on the system. Oh, work in. Whereas clockwise, work by the system. So immediately looking at this curve, and I just drew it, I can tell you that this represents the work what? Pump. It can be of a pump. But it's the work on the system. So this represents the work input to an energy consuming device.
So path 1 was above path, if the first path, the black one was above
Yeah.
the second path, then you would have an energy producing device like an engine or a turbine.
Yes, if it reverses direction, this area would represent the work by the system, and then it would be more representative of an energy producing device, i.e. a turbine, a windmill, whatever it might be. Or if I take this cycle, and so I take the cycle, and now I want to reverse the cycle. Instead of going this way, now I follow the opposite path back, so I reverse the cycle. So if I went this way and came back, and then came back round, and then I decided, hey, let's reverse the cycle, and then I went back, then I would have this area minus this area, which would give me 0. So if I take a cycle and then I reverse it, I end it back up here. There's no net area if it's reversible in this case. So the area within a cycle path curve for a PV diagram represents the work done on or by the system. So this area in a PV diagram. Now if I just go from state 1 to state 2, the area under the curve from 1 to 2 represents the work on or by the system. Now if I say that I come back this way and it's net work on the system because it ends up being counterclockwise, then this represents the work by the system. This area, the green area. And then everything under the red curve represents the work on the system. So I had to put some work in, or work by the system. And so this is work on the system. This is work by the system. But I can break down all those areas. So let's go to the engine example. So I have a PV diagram of an engine. And if I look at what kind of the PV diagram for an engine looks like, it looks something like this. And so you can see here I have a clockwise component. So this is an engine. So I can break this up into different processes steps for fuel intake, whatever it might be. And so then here I compress the gas, then I have combustion, then I have my power stroke, then I remove the exhaust, then I fill it in with fuel, I compress it. And so you can see here that I have a clockwise component and a counterclockwise component. In that. And so this part is the work out, this part is the work in. So if I just plot this and I want to increase the efficiency of my engine, I want to minimize the work in and maximize the work out. So if I make an engineering change and I plot this and I see that this area didn't increase in this one, I know I did the wrong thing. All I have to do is look at this. And I can look at any PV diagram and I can tell you where the energy consuming and energy producing parts of the curves are.